Hey guys, it's me, Dr. Wolf, using a software called Explain Everything to explain the two sections of Chapter 10. I know you're going to be testing this week and next, and you may or may not be attending class to hear the lessons on this chapter. So anyway, Chapter 10, chi-square tests. I'm just on the cover page right now explaining that we'll be working on two sections. 10.1 is an inference procedure called a goodness of fit test. It can help us answer a question like, is there a preferred day of the week to go to the movies? Or is there a even distribution of colors of M&Ms in a bag? Or is there a certain percentage of racial breakdown in a urban city? Second section, 10.2, is a section on the chi-square test of independence. And in this section, we'll be learning how to use a two-way table of expected frequencies and answer questions such as, is there a relationship between smoking and gender? Okay, so here we go. I'm going to flip the page. In chapter 10, we're going to have a formula involving something called a chi-square statistic. You can see the formula right here. Chi-square equals the summation of O minus E squared over E. You will see what that's all about in the upcoming sections. We're going to have some graphing calculator instructions also in the upcoming sections. Okay, flip to page 3. Page 3's got a brand new table that we'll have to learn how to use called the chi-square distribution. And you can see based on its shape that it's a skewed right distribution and also indexed by degrees of freedom and the area and the tail. And this will be used to get critical values for our hypothesis testing rejection region. Flip to page 4. Okay, so the lessons begin, the chi-square goodness of fit test. And it revolves around something that begins with a chance process called a multinomial experiment. So in a multinomial experiment, what happens is there's going to be a fixed number of independent trials, but in this case there are more than 2 possible outcomes for each trial. So if it's day of week going to the movies, there's 7 outcomes that could be your favorite day. The probability of each outcome is fixed and classified into categories. Back in one of our probability chapters, we talked about a binomial distribution, but that was restricted to just 2 possible outcomes. So here are some scenarios then that have more than 2 outcomes called multinomial experiments. A tax prep company wants to determine the proportion of people who use different methods to prepare their taxes. The company can perform a multinomial experiment. It wants to test a previous survey's claim concerning distribution of proportions of people who use different methods. It can compare the distributions of proportions claimed in a multinomial experiment with the previous survey's specified distribution. And to do such a thing, it's going to perform something called a chi-square goodness of fit test. So this chi-square goodness of fit test is going to be used to test if a frequency distribution fits some expected distribution. The null hypothesis is going to state that the frequencies are as specified in that distribution, while the alternative hypothesis states that the frequency distribution does not fit a specified distribution. So here we go. Imagine the tax preparation. Suppose that in some previous survey, it was learned that 25% of people use accountants, 20% of people do by hand, 35% computer software, 5% get friend and family to help, and 15% with tax prep service. So you can see here we've taken this categorical variable, method of tax preparation, and broke it down into 5 categories. So what's going to happen in this goodness of fit test is there's going to be a new survey. And in some new survey, we're going to check to see if the people who are being newly surveyed have a tax preparation distribution that's similar to the one from the previous survey. So the null hypothesis is that the claimed values of those percentages are all as claimed, and the alternative is that the distribution of tax prep differs from that claimed distribution. So in order to decide if we have a different distribution, we're going to calculate again something called a chi-square statistic. And in order to do so, we're going to have to look at some observed frequencies, which come from a survey, and compare them with expected frequencies. Okay, flipping the page. So what we have to do is learn how to get these so-called expected frequencies. So what happens is each of the subcategories is going to have some claimed percentage that goes along with it. And there's going to be a survey that involves n people. So to get each one of the expected frequencies, there's this formula that I'm highlighting in red here. EI equals NPI. So n is just the number of trials, the sample size for our current survey, and PI is the assumed probability in the ith category. All right, so for example, let's say that the tax prep company surveys 300 adults to ask them how they did their taxes. And what they do is they give you a table of results. Broken down into those 5 categories, we have something called a table of observed counts. So these observed frequencies have to be compared with some expected frequencies from the previous survey. And what we do then is we take those 300 people, we take this observed data right here, and we're going to go figure out how many people would be expected. So check out slide 4 here where my red moving dot is. We take 300 times each of these percentages, and we learn that the expected frequencies would be 75, 60, 105, 15, and 45. Just some basic math right there with percentages and counts. And now what a chi-square test is going to do for us is it's going to help us figure out if these observed frequencies and these expected frequencies are significantly different from each other. If so, then we get to reject HO. Okay, so next slides explain the chi-square test, and it's got the process broken down where we are going to get our observed frequencies from a random sample of people. We have a condition that the expected frequencies that we calculate must all be at least 5. And if those conditions are satisfied, we have this new distribution, not normal, not t, but chi-square distribution with k minus 1 degrees of freedom. K is that number of categories, so in this case it's broken into 5 categories. We would have 4 degrees of freedom. And what we're going to do to compute chi-square is, if you look at this summation notation, we have to go to every observed count O, minus off the expected count E, square the result, and divide by E. Then you go to the next observation, minus its expected frequency over its expected frequency. And in this case of the example above, we'd have to do this 5 times and add up all the results. Flipping to page 6. All right, so as usual, the slides that explain this chi-square test look like the previous 2 chapters that we've just been working in. We've got a 9-step process listed out here, and ultimately we're going to fill out, like we've been doing in most of our problems, an A, B, C, D, E type of thing again, where A is going to be us writing the hypotheses, B will be us drawing a critical region, this time a chi-square distribution with k minus 1 degrees of freedom. And then we will be calculating a test statistic, and then we will be making a decision and interpreting that decision in the context of the original claim. All right, so back to tax prep. For tax prep, our assumed model for the null hypothesis is that the method of tax preparation has these percentages: 25, 20, 35, 5, and 15. Our survey results give these 5 observed counts. And we want to know if the observed counts and the expected counts differ significantly. So here we go with the A, B, C, D, E thing. HO, the distribution of tax prep methods, is as specified: 25% accountant, 20% hand, 35% software, 5% friend family, 15 tax prep service. That's our claim. HA, the distribution of of tax preparation differs from the claimed distribution. Alpha, 0.01. Degrees of freedom, 5 take away 1 is 4. Rejection region. Now you have to go to that chi-square table in the beginning of the packet. With 4 degrees of freedom and 0.01 for alpha. I'm going to flip back to that and show you. Okay, I'm not sure how to flip back. So anyway, please, you flip back and go to that chi-square table in the beginning of the packet. And in the beginning of the packet with 4 degrees of freedom and 0.01 for alpha, you should be able to come up with the critical value for that chi-square statistic, the one that's printed small under this picture. Okay? All right, so then we get to the number crunching part of this procedure. And in this number crunching part, we have these 5 observed counts. Those are the O's in the formula. We have these 5 expected counts. Those are the E's in the formula. And here we go, one by one, O minus E squared over E. Next one, O minus E squared over E. All the way down to the 5th row in this table, O minus E squared over E. Add that stuff all up and you get 35 for the chi-square statistic. Flipping to page 7. Okay, so we got that 35.121. It's clearly in this rejection region. The critical value that we found, we are well above that critical value. So we have enough evidence to reject HO. There's enough evidence to conclude that the distribution of tax prep methods differs from the previous survey's results. Okay, so we're going to give you a second example here. And in the second example, a researcher claims that the number of different colored candies in a bag of dark chocolate M&Ms is uniformly distributed. Uniformly means the colors are all equally distributed. So to test this claim, you're going to get a bag that has 500 dark chocolate M&Ms, and you're going to count the frequency of each color. So using alpha equals 0.10, we're going to perform this so-called chi-square goodness of fit test. So after dumping out the 500 M&Ms and counting the colors, we have these. Well, now if these 1, 2, 3, 4, 5, 6 colors were all uniformly distributed, check out what E would be. E would be 500 divided by 6. The expected frequency would just be 83.3 for each of the colors. And we need to know if these numbers right here, 80, 95, 88, 83, 76, 78, if they're significantly different from the expected value of 83.3. So here's the ABCDE thing again to perform the chi-square goodness of fit test. We claim that the different colored M&Ms in the bag are uniformly distributed, and then we're going to test if the distribution is different than uniform. Alpha is 0.10, degrees of freedom 5, flip to the front of the text, front of the note packet, grab that chi-square table, 0.10 for alpha, 5 degrees of freedom, 9.236 is the so-called critical value right here. Okay, time for the test statistic. Again, we have 6 computations to do, 6 of these. O minus E squared over E. Got to do this stuff right here where I'm highlighting in red, and crunch that out to the quantity 3.106. Okay, so now it's decision time. That's going to be a fail to reject HO, because 3.106 is down here in the fail to reject part of the critical region. So we don't have enough evidence to reject the claim of uniform distribution. Now, as you saw right here, this test statistic requires quite a bit of number crunching. So I will show you in class how to do the goodness of fit test in the calculator. To do so, you're going to see me put the observed counts in list 1. You're going to see me put the expected counts in list 2. So this will be list 1. This will be list 2. And then in the stat test menu, there's this chi-square goodness of fit test. It'll output for me the 3.106, and it will output a p-value to help me make a decision for the test. Okay, I'm going to flip to page 8 and show you a couple of examples. All right, in this first exercise, again, the instructions at the top look like previous chapters. we have A, write the hypotheses, B, find the critical values, C, compute the chi-square statistic, D, decide if we can reject HO, and E, interpret the decision. Okay, so this one's about coffee drinking. A researcher claims that the number of cups of coffee U.S. adults drink per day are distributed as shown in this figure. So there's a little pictogram for us right here showing the percentage breakdown of the ways that adults drink coffee. So I'm going to randomly select 1,600 adults and ask them how many cups of coffee they drink per day. And these are my observed results from the 1,600 people. And my job is to test the researcher's claim that the percentage breakdown of adults that drink 1, 2, 3, or 4 or more cups are these percentages right here. Okay, so I'm going to write on this slide, and then I'll be back in a moment to explain. Okay, so what I've written so far, and it wasn't as easy as I thought to write on this, is I don't really have room to write out HO and HA. But you can see that on the Smartboard file once I post it. So HO are the percentages of adults who drink 0, 1, 2, 3, or 4 or more cups of coffee are these percentages. HA is that the percentage of adults who drink these numbers of cups of coffee differ from the claimed distribution. So you just write sentences here. Part B, the critical region. I have a chi-square with 0.05 in the upper tail. 9.488 will be the critical value you look up on the table that's in the front of our note packet. There are 4 degrees of freedom because there are 5 subcategories for how many cups people drink per day. So the work I have to do is realize that the table gave me these O's, the observed frequencies, and I have to calculate the E's. So there's 5 calculations I have to make based on the percentage in the pictogram. This is how many people I'd expect of my 1,600 to answer in these categories. So as you can see, each of these E's and O's are slightly different from each other, and the job of chi-square is to see if this set of 5 numbers is significantly different from this set of 5 numbers. So in order to do that, I have to do the summation of O minus E squared over E. And what that looks like as we start to calculate it would be for the first category, the O is 570, the E is 576. I have to square that, divide by 576. Okay, and then I'm going to have to make 5 of these in chi-square. So I'm going to put plus, ... plus, the last one is going to be 164 minus 160 squared over 160. And when I take those 5 things and add them up, we will have our chi-square statistic. But to do this work right here, let me convince you that rather than set up all this work right here, let's go and do some calculator stuff. So at this point, I'd like you to type the 5 O's in list 1, these 5 E's in list 2, run chi-square GOF test in the stat test menu, and we will have a chi-square statistic. So I'll be right back with that. Okay, so I'm done with the calculation, and my calculator is reading out 2.81 for the chi-square statistic, 2.81, and it's reading p-value equals 0.5893. So it's decision time, right? This is part A, our hypotheses, part B, our critical region, part C, our test statistic, and now I'm ready for part D, which is going to be fail to reject HO. And because I'm failing to reject HO, and HO is the claim, I do not have enough evidence to reject the claim that the percentage of coffee drinkers are as specified in that distribution. Okay, so I think I'm a little bit out of room to write that, but please feel free to check the Smartboard and also check the Smartboard file for exercise 16. Thanks, hope that helped.